All right, so let's look at something like this here, where in a right-tailed test, the sample size will be 24, and we'll do a test statistic of t equal to 3.714. All right, so let's do the actual p, which is what you are going to actually be expected to do. So basically, since n is 24, your degree of freedom is going to be 23. And since you're dealing with 23 degrees of freedom, you will just do TCDF from 3.714 to 10 or 100, but with 23 degrees of freedom, and you get 5.7 times 10 to the negative 4, or basically 0.00057. Now, for the range, so to speak, look for t equal to 3.714 with 23 degrees of freedom. So look for 3.714. So what I'll do is, now, how many degrees freedom was that? 23. So 3.714, it's very close. It's going to be right in here. So it's between where t is going to be 3.768 and where t is going to be 3.104. So since this is right-tailed, you look for the one-tailed areas, and it's going to be between 0.0005 and 0.0025. So the area is going to be between these two. Now, you're probably wondering, why can't I just get it directly? I mean, yes, you will be able to get it directly. I'm just trying to show you an appreciation for the way your older relatives would have done this back in their days, so to speak. So now let's see here. So if we're going to do a two-tailed hypothesis test where we'll do it with a sample of 32, and I'll give you a negative test statistic of negative, let's see, 3.109. So here's the thing. In a two-tailed test, your t can be both positive and negative. I mean, positive or negative for that test statistic. So what we're going to do here basically is if we did negative 3.109, this is 31 degrees of freedom. This is where you would do 2 times, let me read, yeah. So basically in this case, folks, you would do 2 times TCDF from negative 10 to negative 3.109 with 31 degrees of freedom for the actual p-value. So if we figure out what the actual p-value is going to be for this, negative 10 to negative 3.109 with 31 degrees of freedom, and we get 0.0040. And for the range, you would look for t equal to 3.109, 31 degrees of freedom. But you would actually want to find it where, so yeah, 3.109, 31 degrees of freedom. And it's going to be right in here. So I'm not going to write it out this time, but it's going to be between 0.001 and 0.005. And I just got to find this place. Sometimes this technology doesn't work the way I want it to. Yeah, 0.001 and 0.005, two-tailed. And it fits the thing here. Now, I would not ask you this on a test, and you're probably wondering, then why are you doing this? Well, basically, what I'm trying to hopefully impress on you here is, give you a bit more of an appreciation for how it used to be done back in the old days. So we're going to skip over this one. So basically, we can do a t-test for a mean, provided we don't know the population standard deviation. And in reality, that's how it's really going to work. Now, did you know that you can find the point estimate when given a confidence interval? So for instance, if I give you a confidence interval such as 74.25 to, let's draw a little bit nicer one there, mu to 81.43. So in this example here, now you remember, confidence intervals for the means, and for that matter for the proportions, are actually going to be symmetric. So basically, the margin, the point estimate is in the center of this. And in other words, basically to find that, you literally take the average of these two. And we get 77.84. Now, for the margin of error, that's just as easy. Because here's the thing, if you took 77.84 and subtracted 74.25, you get this. If you did 81.43 minus 77.84, you get the same thing. Therefore, your margin of error is 3.59. Now, I always like to ask a question like this, even though, arithmetically, it's actually ridiculously easy. But a lot of people tend to miss this question that is otherwise very easy. So, but another way you could do this would be to take, if you did the whole distance and divide that by 2, that gets you your margin of error that way. So yeah, basically your point estimate, which is the sample mean, is 77.84. Your margin of error is 3.59. Now, what you'll do here, let's try another example. Now, it's going to work the same with proportions, except for proportions, the point estimate will be a proportion. So 103.75 to 105.13. So basically, you can do the point estimate and the margin of error. So you could do the margin of error first, if you really want, by taking 105.13 minus 103.75 and dividing it by 2, and you get a margin of error of 0.69. And if you were to add 103.75 plus 0.69, or 105.13 minus 0.69, you get 104.44. So that's all there is to that. Now, the next thing we're going to do is figure out sample size required. Now, this formula is the critical Z times, see, we're going back to, because we don't know N, because we know nothing about N, we will use large degrees of freedom. So, and you always have to round up. So in other words, if you don't round up, if you round down, it's not going to be enough. So what I mean by rounding up, we'll see here. So assume we want to estimate the mean IQ score for the population of stat students. We don't know what N is, but since we have 99% confidence, we go to 99% confidence and choose 2.576. And your margin of error is going to be 8, and your standard deviation is 15. So basically, you have to take this 2.576 times 15 and divide it by 8 and then square it. A lot of students honestly forget to square it or round up. You will lose points if you make that mistake. So if we figure this out, 2.576 times 15 over top of 8, and then you square it, we get 23.32. And here's what I meant by round up. You have to do N as 24. It's not 23, and especially not 23.32. This always has to be an integer. If it's not an integer, you're going to be marked wrong. So don't do that. So with that in mind, let's say we have a standard deviation of 15.8 and a margin of error of 3.5. So the only thing that's going to really change here amongst all of this is going to be the critical Z value. So for 85%, you would use, it's going to be critical Z times the standard deviation over your margin of error and squared. So if you go to 85% confidence, 85%, the critical Z is 1.44. Times 15.8 over top of 3.5, and again, do not forget to square it. And so when you square this, what's going to happen here? Let's see what that's going to give us. So open up a parenthesis and type this out, 1.440 times 15.8 over 3.5. And again, do not forget to square it. We get 42.25, but it has to be 43. So that's what that's going to be. Now, for 95% confidence, let's do that one. So for 95%, your critical Z will be 1.96. Times 15.8 over 3.5, and then you square that. So basically, all we're doing is we are going to change this to 1.960. And we get 78.28, or n equaling 79. Lastly, if we do 98% confidence, 98% is 2.326 times 15.8 over 3.5, and then you square that. So I'll just kind of highlight that. And we get 110.25. N is going to be 111. So you can look, you'll definitely get some of these sample size calculation questions on the test. So beware of that. Now we're going to do a real world test example. And then what we're going to do is we're going to do confidence interval. So suppose the hourly wages of retail workers is claimed to be $18 an hour. So you have reason to believe that it is actually going to be lower. So a random sample of 31 retail workers yields a sample mean wage of $16.74. So the null is going to be where mu, and you're going to have 18 here. And by virtue of the fact that it flat out says this, and the mean is actually lower, you're going to go less than. Now, keep in mind, when you're writing hypotheses, it has to be 18, has to be the same value, greater than or equal to, or mu equals 18. So we have the sample mean of 16.74. And then we'll have the sample standard deviation. So basically, we're going to calculate this test statistic, which is your sample mean minus the claim mean over this. Now, because this is a left-tailed test, we know that this t-value will be negative. So if you did 1674 minus 18 over top of 226 over the square root of 31, and we can do this in the calculator, and I'll even show you how this can be done on the calculator straight up. (2.26) over square root of 31. This is going to be negative 3.104. Now, that's your t statistic or your test statistic. Round it to 3 decimal places at minimum. Now, since n is 31, alpha was 1 and 30 degrees of freedom, and it's going to be 2.457. But since this is left-tailed, the critical value would be negative 2.457. But here's the thing. That critical value for t is going to come back into play when we do the confidence interval. So here's the thing. We determine the p-value, and here's negative 3.104. You are going to reject the null. And by virtue of the fact that you rejected that null, the conclusion would be very simple. Based on our data, we went with the alternative and that we have evidence, evidence that the true population mean hourly wages of retail workers is actually below 18 per hour. Now, if you failed to reject the null, so we have evidence. That doesn't make it so, though. We just say we have evidence based on our data. That's how you present it in the real world. So keep this in mind now. Alpha is going to be 0.01, and you wanted the area in one tail, so it's going to be 98% confidence. So basically, the margin of error to the nearest penny, that's 2 decimal places for you and me. Now we get the critical t-value of 2.457. Now you'd want to use the positive version for this. And you multiply that by 0.26 over the square root of 31. So yeah, nearest penny means 2 decimal places. So when you do this, I don't even know if I need to close that parenthesis, but wow, it is $1 right on the money. So the confidence interval is your sample mean minus that. So 1674 plus or minus $1, 15.74 to 17.74. Now, if you notice, this entire confidence interval is below $18. No need to point this out. The entire confidence interval is below $18. So based on a sample of 31 retail workers, we are 98% confident that the interval from $15.74 to $17.74 captures the true population mean hourly wage of retail workers. So now, if we want to do this in the calculator straight up, this time we're going to go to stats here. Now the claim mean was 18. The sample mean was 1674. Standard deviation was $2.26, and we had a sample of 31. Now the alternative hypothesis is less than. So this is kind of just extra here. And we figure out the p-value, and it gives you everything here. Now, now you have to go to t-interval. And if you notice, the only thing we've got to change here is make this 0.98. And again, make sure that is t-interval. And then when you carry it out, now the drawback to a calculator is, calculator doesn't know that you're dealing with pennies here. So in other words, basically since you're dealing with pennies here, that's what you're going to get. All right, so with that in mind, what we're going to do here is we're going to do this for the t-test. We're going to see the marriage between the t-test and the calculator, and you think it's lower. Now, the thing is, and we're basically